Okay, so this is the last topic in probability, and it's called conditional probability. So what is this about? Consider a Venn diagram. Oops. Suppose the sample space is S, and we have two events, event A and event B. Sometimes we just want to find the probability of A, so P of A. Other times we have additional information. So what if we ask, what's the probability of A? But now what if we have an additional piece of information? What if we know that event B has already occurred? And that's called the probability of A given B. And we write P of A with a vertical bar and then B. So this means, what's the probability to observe event A given that we know that event B has already occurred? So the question is now, how do we compute this? Well, if we know B has already occurred, S is no longer the sample space, right? The sample space contains all possibilities of an experiment, but because we know B has already occurred, B is our new sample space. So then event A, the part that's outside of B, no longer exists because we know event B has already occurred. So all we're left with is the part of A that's still inside of B. So that's the probability of A intersects B, what's common to A and B. But there's something missing here. If you remember, the area of the sample space has to be equal to 1. So initially the area of S, the rectangular region, was 1, and you can see that the probability of B, the area of B, is much smaller than the total area of the rectangle, which is 1. But when we say P of A given B, B is the new sample space. So the area of B should be equal to 1. So the question is, how do we rescale the region to make it become a region of area 1? So suppose that the probability of B was simply 0.3. Well, the idea is, by which factor do you rescale this region to make it so that the area of the region B becomes equal to 1? Well, rescale by the same amount. If you divide the area of B by itself, then the region becomes a region of area 1. So you can rescale the region B to have an area of 1 if you divide by its area, by P of B. And that's how you find the conditional probability of A, given that B has already occurred. Now a nice result from this is if we isolate the probability of A intersects B by multiplying both sides of the equality by P of B, we have this other nice result, that P of A intersects B equals P of A given B times the probability of P of B. Okay, so this is how we find conditional probabilities. P of A given B is P of A intersects B over P of B, and we can find the probability of an intersection if we know the conditional probability. So what rules do we have with conditional probability? Well, there are three main results. The first one is the complement rule. So let's look at a second Venn diagram, and keeping in mind P of A given B is just P of A intersects B over P of B. So look at this Venn diagram. And remember the partition theorem. Suppose you have two events, event B and its complement, so everything else. And consider event A. Then let's ask, how can we find the probability of A? Well, if you remember, we want the area of A, but we can find the area of A in two different pieces. First, adding the area of this part, which is the region common to A and B, so P of A intersects B, plus adding up the area of the second part, that's P of A, intersects what's common with B complement, so P of A intersects B complement. Now the idea is, why do we want to go from here to conditional probabilities? Well, the reason is simple. When you look at P of A given B, you know that B has already occurred. That is one additional piece of information. And the more you know about a problem, the easier it should be to solve it. So the idea is, it's a good idea to go from an intersection to a conditional probability. Given that we know that B has occurred, this should be easier to find than this. So let's see. P of A intersects B. Well, that's just P of A given B times P of B. Plus, and now this result is true for any event B. So we can replace B by anything we want. Well, here we are replacing B by B complement. So P of A intersects B complement will be P of A given B complement times P of B complement. And that's equal to P of A. And this result is called the law of total probability. And you see what happens is we say, well, we want P of A, and this is how you should think of it. We want P of A, and we will condition on all possibilities. Here, we split it up, the sample is split into two parts, B and B complement. So P of A, well, we will condition on the first option, so P of A given B times P of B, or, well, if it's not B, it's B complement, so or plus, and now we condition on the other option, P of A given B complement, P of B complement. You could split up your sample space into more than two parts. Suppose you split up your sample space into n parts. So you'd have B1 as your first part, B2, B3 up to Bn. So you can extend this result and say P of A would be, well, now condition on the first possibility, P of A given B1 times P of B1. So B1 is your first possibility, or plus P of A given the second possibility B2, P of B2, plus up to, suppose you have n possibilities, conditioning A onto the nth and final possibility. And that's an extension. But for us, the key result will be this one, conditioning on an event or its complement. All right, so what other result do we have? Well, we also have the complement rule. So remember that for basic probabilities, P of A is just 1 minus P of A complement. And the nice result is this also works with conditional probabilities. So let's see how this works. Suppose I say P of B. Well, now we'll use the partition theorem. So it's P of B intersects with A, or P of B intersects with everything else, A complement. Now, what I'll do is I'll subtract this on both sides, and I'll isolate P of B intersects A. So P of B intersects A will be P of B minus, I'm sending this on the other side, so minus P of B intersects A complement. Now the idea is, well, B intersects A is the same as A intersects B. B intersects A complement is the same as A complement intersects B. So I'll flip them around. P of A intersects B equals P of B minus P of A complement intersects with B. And now let's assume that the probability of B is positive. Then we can divide across by P of B. So let's do so. So over P of B, over P of B, over P of B. And now think of it. P of A intersects B divided by P of B, that's the probability of A given B, equals P of B over itself is 1 minus P of A complement intersects B over P of B, that's the probability of A complement given B. So that's the complement rule. And you see it also works with conditional probabilities. Before, it was just P of A equals 1 minus P of A complement. And you see the result is the same here. P of A equals 1 minus P of A complement. The only difference is both times we condition on the same event. So we have the complement rule for conditional probabilities. And the very last result is called Bayes' theorem. And so here's the result, and then we'll look at why it might sometimes be useful. And this gives you a way to invert conditional probabilities. Suppose you want P of B given A. So given that A has already occurred, what is the probability that B will occur? Well, sometimes it's easier to find the opposite, P of A given B. And here's what Bayes' theorem tells you. P of B given A, you can flip the order of the two events, is P of A given B times P of B divided by P of A. And that's it. That's Bayes' theorem. So how should you use it? Well, every time you want a probability of B given A, and you know the probability of the reverse of A given B, use Bayes' theorem, and you're good to go. Well, let's prove this. And all we have to do is go back to the definition of the conditional probability, right? Look at the left-hand side. The left-hand side is P of B given A. And this is by definition the probability of B intersects with A. Now because A is the new sample space, because we know A has already occurred, we have to rescale and divide by P of A. So that's the left-hand side. Let's look at the right-hand side. We have P of A given B times P of B over P of A, right? P of B over P of A times P of A given B. Well, by definition, P of A given B is P of A intersects with B. But again, B has already occurred. It is our new sample space. We have to rescale by its area, which is P of B. And we're left with P of B over P of A. And if you notice, well, we can cancel the P of B over P of B, and we're left simply with P of A intersects B over P of A. But notice that the left-hand side is P of B intersects A over P of A, and this is P of A intersects B over P of A. But B intersects A is the same as A intersects B. So both sides are equal, so we have now Bayes' theorem. The following 3 videos will be examples of all of these 3 results.